Yes, thank you. Thank you. So polymer metamaterials. So I'll continue. The order structure of the microspheres was formed during the self-organization of polystyrene particles from the suspension under the action of pressure gradient caused by the convection over Rayleigh-Benard processes. To do this, a drop of suspension containing the optimal content of the dispersed phase and the required amount of the surfactant, which was sodium dodecyl sulfate, was applied to a clean, dust-free substrate from a polycarbonate of specified dimensions. After that, the sample was placed in a preheated drying oven with a forced convection. The surface on which the future sample was located was massive and decoupled from the main cabinet structure to reduce the effects of external vibrations produced mainly by the fan rotor inside the cabinet itself. The resulting samples were numbered and weighted. The quality criteria were good adhesion of the package of the substrate, uniformity of color and thickness of the crystal, and the absence of significant defects at the macro level. Since the resulting polystyrene microspheres will be used in the future to create sensors for an optical response to external influences, one of the most important product parameters will be a narrow particle size distribution. After self-organization of disparate elements of a dispersed system in a single organized array having a periodically specified refractive index. This is what determines the presence of spectrally selective reflection, which is perceived by a man as the color of a structure. This parameter is measured by electron microscopy and dynamic light scattering. Here, so one moment please. Yes, here we see the reflected radiation from the photonic crystal. If you put some substance on the surface of the photonic crystal, we can see the spectral shift of the reflected irradiation from the surface of the photonic crystal. Here we see the spectral shift of the reflected radiation, and here we can see the reason why it has happened, the spectral shift. We see that the photonic crystal is the diffraction grid with a periodic changing of the refractive index. And now if we see the changing of the distance between the neighbored microspheres, we see now the spectral shift here. Now we can see the clip which shows the spectral shift of the reflected radiation if we put some substance, for example, non-polar solvent as toluene, N-octane, or something organic solvent, and we see the spectral shift of the reflected radiation from the surface of the photonic crystal here. It was found that after eliminating the exposure, the position of the photonic bandgap is almost completely recovered. This fact allows to carry out the chemical cycles of the online environmental monitoring. However, the exposed aromatic solvents, sensor degradations is observed, but its linear direction should be noted. So this slide is showing the changes of the spectrum of the reflected response from a photonic crystal under the cyclic action of toluene on its surface. With an increase of the dose of substance acting on a photonic crystal, irreversible changes can occur in the latter, which are expressed of the degradation of the reflected signal from its surface. The absence of the spectral selective reflection from the surface of the photonic crystal has been observed due to the chosen dosage of the applied analyte. Such image blurs may indicate friability of the microsphere surface after treatment. For a more detailed analysis, an attempt has been made to simulate the microspheres of the photonic crystal by an analyte. For this purpose, polystyrene microspheres of sizes 6 till 200 micrometers with a low divinyl benzene content have been chosen as the model for testing. After treatment with the analyte toluene, the dynamic behavior of the microspheres have been recovered by the optical microscope. Observations have been shown changes in the integrated transmittance coefficient of the visible radiation through such microspheres. These changes may relate to additional light scattering from the surface of the microspheres. Such scattering is caused by inelastic deformation of microspheres during the swelling, caused by analyte diffusion and followed by the evaporation from them. Images of swelling and compression of polystyrene microspheres after injection of the analyte are presented below. Next slide shows the swelling of microspheres, and this slide, slide 12, shows the swelling of microspheres and shows the picture of reverse compression of microspheres. This slide shows that microspheres no longer return to their original state. The studies have shown that annexional deformation of polymeric films with a thin layer of hard coating applied on them is accompanied by the following general phenomena. The appearance of regular micro-relief and regular destruction is encoded. It has been found that micro-relief is always oriented along the axis of the tensile of the polymer supports and is positioned perpendicular towards the cracks of the damaged coating, respectively. Observation of processes in model systems of polystyrene microspheres with sizes of 6 to 100 micrometers can lead to a number of conclusions with their behavior after the application of analyte vapors. So, when analyte vapors are injected with a low quantity of divinyl benzene in the polystyrene microspheres, the microsphere surface creates additional friability during the swelling and during evaporation of the analyte. The surface of the microspheres becomes friable. The effect reduces the spectral efficiency of the diffraction reflection from the surface of the microspheres. The structure of the microspheres loses firmness when the analyte is evaporated. If the microspheres are self-organized, they may become depressed. An example, one microsphere presses into the other. This may lead to a depth reduction of strokes as a composed reflected diffraction grating during the interaction with coherent waves that reduce the efficiency of its reflection. The line crossing between microspheres for observation of diffraction patterns are becoming less distinct and, in other words, smoother. This situation also reduces the efficiency of the spectral reflection from the surface of the photonic crystal. In our case, the fundamental question is the formation mechanism of an anomalous structure from microspheres 6 to 200 micrometers in size. Out of the focus of scientific research, audit structures from polymer microspheres of 6 to 100 microspheres in size and methods of their formation still remain. Slide 14 shows the photographs of self-ordering formation of 2D flat layer from polystyrene microspheres. So we can see now the formation of ordered structure of polymer particles on the surface of water. The dispersion of ethanol water with polymer from polystyrene microspheres were embedded on the water surface with the different concentrations of ethanol. And from the different concentration, we can see the different ordering packing of the microspheres on the water surface. Ethanol has a low heat of vaporization, low surface tension, and high pressure of saturated vapors. Good soluble in the water. The rapid evaporation of ethanol from the water surface causes mass and energy transfer flows that can be divided into horizontal convection, Marangoni heaps, and vertical laminar. Marangoni heaps convection occurs due to the gradient of the surface tension of the liquid phase, water, and ethanol in the applied suspension, water-ethanol mixture. The effect consists in a non-equilibrium flow of mass transfer of the dispersed phase, polymer microspheres, along the horizontal surface of the interface boundary of liquids. Due to Marangoni heaps convection of the thin layer of matter, the microspheres are transported along the liquid phase boundary, forming a monolayer of microspheres. At the same time, the microspheres move in a vertical direction. Convection intensity can be controlled by changing of the concentration of ethanol. The processes stop after evaporation of ethanol from liquids interface. They can last for a fractional of a second. An important role here is played by horizontal capillary electric forces between microspheres. The material of the microspheres, polystyrene, is hydrophobic, and attractive forces arises between the microspheres on the surface on the bottom. To obtain a stable system, the occupied surface area of microspheres tends to a minimum, and microspheres tend to occupy the most dense configuration. Here we can see the dependence of packaging quality from the angle of applying the water ethanol drop or suspension on the surface of water. This slide shows the attaching the ordered structure to a hard surface by vinyl 3 toxic solvents. This slide shows just 2D flat photonic crystals from microspheres of sizes for 20 microns and 31 microns. But a new the appearance of flat ordered structures were shown just on the previous slide, sorry, here. But an important issue of the analysis of the ordered structures is the assessment of their packaging quality. To create medical test systems, metamaterials, and other similar products, substrates with a deposited monolayer of cross-packing polymer microspheres with a maximum defect-free structure are required. Moreover, the resulting package consists of domains with different areas. Inside the domains, the packaging could be considered flawless. We discussed the creation about the quality criterion for flat hexagonal packings. However, such a criterion is of little use in the analysis of the significant batches of packed structures of packaging, the size of which is hundreds of times larger than the field of view of the microscope in which such packaging is observed. The size of the domain area can be characterized by the length by length of the chains of microspheres of the site falling in the field of the view of microscope. For hexagonal packing, 3 main directions can be distinguished along which the length of such a defect-free chains is calculated. After determining the main directions of the calculations, the length of the continuous chains LE are estimated in the units of the number of microspheres over the entire area of the photo. The number of such chains with the same length is calculated. Then, using the formula 1, the calculated data LE calculate the normalized packing factor. The physical meaning of the coefficient can be denoted as product of the number of particles unpacked in chains of length LE relative to the total number of particles and the relative change length L. So, on slide here, we see the example. We represent the ideal packing and show the calculated meanings of the flawless packing factors here. Next slide represents the example of photos of photonic crystals with the diameters of 55 microns. And here, on next slide, represents the packing coefficients. One of the possible applications of photonic crystals formed from sub-millimeters microspheres in their use in the form of radio emission sensors, in particular for terahertz wavelength range. The accumulation of photonic crystals in the visible and terahertz range suggests similar physical principles for the selective reflection of radiation according to the Bragg-Snell law. On its basis, the frequencies of the terahertz range should correspond to the sizes of the microspheres at the level of 6 till 200 microns. However, such selectivity upon reflection from a photonic crystal consisting of the microspheres of the sub-millimeter size range is not obvious. To study the selectivity of reflection from surface of photonic crystal, it is necessary to affect its surface from broadband terahertz radiation. With a narrow band terahertz receiver, the intensity of the reflected radiation can be measured. Using the inverse Fourier transform, the spectrum of the reflected radiation is measured and compared to the incident broadband spectrum. Scheme of experimental device is presented on the slide here. Typical generation and detection of terahertz radiation ultrashort laser pulses presented on the slide. In this circuit, the laser beam of a femtosecond laser is divided into two, a pump beam and probe test beam. A more powerful pump beam is used to a terahertz pulse generation. Generation occurs as a rule as the effect of laser pump pulse on some crystal or special structure. The probe beam is used to detect terahertz momentum. For detection, a crystal or structure can be used, similar to that used in generation. Detection is due to changes in some characteristic to the probe pulse in the presence of the terahertz pulse. Common to all mechanisms is the coherence of optical pulses, pump and probe, and terahertz pulse. Under coherence, in the case, we understand the relationship of the phase in the terahertz pulse with a certain characteristic of the optical pulse. This connection is highly accurate, constant in time. Fluctuations in the repetition rate of laser pulses or mechanical vibrations are the same for terahertz and pump pulses, and therefore do not violate this coherence. Pumping pulse and probing momentum are replicas of the sum momentum, and therefore also retain coherence. Thus, the terahertz and probe pulses are tied to each other in phase. Thanks to the binding, the probe pulse interacts in the detector with each time with the same terahertz sine momentum. The duration of the probe pulse is usually tens femtoseconds, which is much shorter than the terahertz pulse period, from 3 to 1,000 femtoseconds. Therefore, we can assume that the probe pulse interacts with the some permanent field. By introducing a time delay of the probe pulse along the relative to the pump pulse, you can select the relative time of arrival in detector of probing the terahertz pulses and detect different parts of the pulse with the time resolution corresponding to the duration of the probe pulses. Scanning time delay interval using the mechanical delay line, it is possible to obtain a waveform oscillogram on a terahertz momentum. To extract spectral information, apply to the waveform Fourier transform. To increase the sensitivity of the circuit, the pump beam modulate using a mechanical chopper modulator and detect terahertz pulse-induced modulation of the probe beam by synchronous amplifier. This slide shows the photoconductive antenna, which consists of two metal electrodes located in some distance from each other on a semiconductor substrate. High voltage applied to the electrodes several kilovolts. When lighting the gap between the electrodes with ultra-short laser pulse concentration of charge carriers of the semiconductor sharply increases for the short time of the order of units of 10 picoseconds. For effective absorption of laser radiation with the release of energy carriers, laser photon should exceed the band gap of semiconductor, but sometimes multi-photon absorption is also used. A rising free media is accelerated by the field applied to the gap, as a result of which there is a short-term current pulse, which is the source terahertz radiation. Thus, an ultra-short laser pulse serves ultra-fast switch for the antenna, converting it from isolating to a conductive state. The duration of the current pulse and the spectrum emitted terahertz wave is determined mainly by the carrier lifetime semiconductor. So, here we see the results of our experiments. Just we see that the red color is our induced light of terahertz range, which was fallen on the surface of the photonic crystal, flat photonic crystal, which was made by polystyrene from polystyrene microsphere of the sizes of 200 micrometers. The blue color is the reflected light from the surface of the photonic crystal. So we want to prove that the band of the irradiated radiation is much more error than induced irradiation. So the behavior of terahertz radiation is very much similar to the radiation of the visible range radiation of the surface of the photonic crystals of visible range, when the sizes of microsphere is in nanoscale. So I skip the slides and just read the conclusions. Using photonic crystals, the possibility of detecting objects in media is shown. For microspheres with sizes 6 till 200 micrometers, the possibility of using 2D ordered structures in photonics of the terahertz wavelength range is shown. Packed structures make it possible to obtain spectrally selective reflection in the range of 100 terahertz till 1000 terahertz, depending on the structure of the package and the size of the elements. The introduction of metal complexes of organic dyes allows us to selectively shift the frequency of the reflected radio emission. And the tuning and photoconformation of the dyes allow the tuning of the output radio emission for the given coordinate.